Hello, I'm Bill. I'm the video man here today. Good luck on this problem. It's a doozy.
Here's my brother Doug. Hi, Doug.
What's happening, y'all? Good luck.
Of course, we have to show Kitty. Where's there? There's Kitters. There's Kitters. There we go. We'll go back to my brother. We can inquire. We'll do a little interview with him another time about the hair. And but today,
What's wrong with my hair?
I'm just teasing. Today is problem number 63 from section 6.3. As Don would say, it's not the calculus, it's the algebra. And I can hear Pam in the background going, we can do this. And I see Sean smiling going, yes, another calculus problem. So thank you, Miranda. Miranda asked for this problem to be done. It does take quite a bit. I also did post notes of the work all worked out just in case you need that. And this problem is actually very much like one you would see on the AP exam. So I thought it was a great question that Miranda had. So you have your books open, section 6.3, number 63, and it's called weight gain. A calf weighs 60 pounds at birth and gains weight at the rate of change of weight with respect to time equals K times 1200 minus W, where W is the weight in pounds and T is the time in years. And it says solve the differential equation. Okay, so we're going to go ahead and do that first. That is the most difficult part. Please notice, first of all, that K is a constant. I'm going to have to try a different color here. I don't think that's dark enough.
It's not.
There we go. So K is a constant. So we are treating it as a constant, not as a variable. Okay, so let's go ahead and get this problem started. The first thing we need to do to solve this differential equation is I am just going to write it vertically. There we go. And what we have to do here is have a separation of variables. So the first thing I'm going to do is I am going to multiply both sides by dt so that we have separated the variables of integration. The next thing I have to do, though, is notice we have a w with the dt, and so we have to separate the 1200 minus w so that it is with the variable of integration dw. I can't add or subtract 1200. That is not the relationship between variables and variables of integration. I have to divide both sides by 1200 minus w. I am going to leave the k on the right because on the left I just want as small as expression as possible. So we now have 1 over 1200 minus w times dw equals k dt. The next thing we have to do is we're going to integrate both sides because we are solving for w. Notice that my expression on the left here probably could use a u substitution, and so I am going to do that here. It's easier if I kneel down. So here we go. We are going to make our u equal to 1200 minus w. That means our du would be a negative dw. When we take the derivative, I do not see a negative here in this expression, so we're going to multiply both sides by a negative so that our substitution is exact. So let's come on up over here. There we go. On the left now, we have 1 over u, and we will replace our dw with a negative du. Now, if it's okay with you, on the right-hand side, we're pretty good at this. That is KT, and of course, we would never forget what, Ethan? The C plus C. All right, we still have to integrate the left though, but we recognize this. The integration of 1 over u is the natural log of the absolute value of u. So here we go. We have our negative out front. We have the natural log of the absolute value of u. Our u is 1200 minus w. And we are just going to rewrite the expression that's on the right. Okay, the problem we have here is we need to solve for w, and we have a whole bunch of stuff with it. Okay, the first thing we're going to do, here's where it gets a little tricky, so stick with me. Let's get rid of this negative. I want to raise both sides with a base of e, but this negative is in the way. Okay, so we are going to multiply everything by a negative. That sounds okay, doesn't it? Sounds just fine. Except for, notice this expression is positive. This expression is now negative, and you're expecting me to write plus a negative c. It is not. It is still plus c. How come? Because if I multiply here by a negative c is still a constant. It's still plus c. It is still a constant. Okay, now we can exponentiate both sides. There we go. This causes the natural log to eliminate, and also the absolute value signs. And we have 1200 minus w equals, all right, I'm going to be a little careful here. Notice that this expression using exponent rules is e to the negative kt times e to the c. Right, here are our exponent rules. All right, gonna get a little lower here. Gonna leave the left-hand side the same. There we go. Notice e to the c is still just a constant. And e to the negative kt, I wanna eliminate that negative exponent. I'm gonna move it to the denominator as a positive. Good Lord, we are done with our calculus way back here, and we are still just working our way through this. Thank you, Miranda, for asking this question. Now, the next thing I'm gonna do, if you don't mind me doing this in 2 steps, I'm gonna subtract a 1200 from both sides and then multiply everything by a negative. And so, in 1 step, what we'll end up with is w equals, see, that would have been a negative 1200, now it's positive 1200 minus c over e to the kt. Okay, so what we have right now is w equals 1200 minus c over e to the kt. We need our c. Where does that come from? If you notice, when you go back to the original problem, it says a calf that weighs 60 pounds at birth. They gave us an initial condition, a point in time. They told us that when the time is 0, that the weight of the calf is 60. So we can use this information to get our C right here, right? So we're gonna put 60 in for the weight, and we are gonna put 0 in for the time. And we are gonna solve for C, and then we'll have our final differential equation. Then we can move on to the other problems, A, B, and C that we have. Let's take a look here. 60 equals 1200 minus C. Notice when you put a 0 in for the time, that is e to the 0, and anything to the 0 power is what? Do you know, Doug or Bill? Anything to the 0 power is what?
I don't have a clue.
It's 1.
One.
Yes, it's 1.
Yeah.
It's 1. Very good. So we have a 1 here. So
It took a second to think about it, but yeah.
Well, that was really good though, Bill.
I come from behind sometimes.
You do well. So notice here when you solve for C, obviously this C, 1200 minus what number? 60 must be 1140. So our final result for our differential equation is 1200 minus 1140 over e to the kt. So that we solve the differential equation. Now, we're gonna keep moving here. When you look at A, it says use a computer algebra system. That would be me. I'm the computer algebra system. To solve the differential equation for k equals 0.8, blah, 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 blah. And I just asked you to do 0.8. So we're just saying k is 0.8, and we're gonna pop it in right here. That is the only value of k we're gonna use, because obviously this problem is long enough. So what I'm gonna do now, I'm gonna leave the words, I'm gonna erase the board, and I'm gonna bring this up over to the left, and we're gonna start using this equation right here. So let's get rid of everything.
You want me to pause?
No, there's no pausing.
Okay.
So we have to keep going. So Bill, tell me what you have going on while I'm erasing. Talk to my kids.
My teaching partner and I are Zooming with our 4th and 5th graders tonight, just to see how they're doing, and we're also tackling parent questions, because right now, Chippewa, we are only doing online language and math for our 4th and 5th graders. So we are just going to make sure they're on the right path, take any parent questions, and give them all the work that they need for the rest of the week tonight.
That's awesome. I'm sure they're super excited. Doug is going up to our cabin in Lexington today. Doug, what do you plan on doing up there?
I'm gonna jump in the water.
And you think he's joking, people.
He's
not.
going in.
He's going in. We call him Polar Doug.
There's a lot of minerals. It's good for the body.
So you know what I might do then? If he does that, I will try to post a video of that so you can see Polar Doug going in.
All right.
All right. So let's see, class. We are now on B. If the animal is sold when the weight reaches 800 pounds, find the time of sale. Okay, and again, that's for just k equals 0.8. So again, what they were asking for on B is at what time will the animal be sold if it weighs 800 pounds at that time. So we're going to substitute in an 800 for our W, and then we're going to solve for the time when that happens. So notice there's really nothing that has to do with calculus here. This is just solving for t. But of course, it's not in our favorite form, I'm sure. There we go. So let's work on solving for t. We'll subtract a 400 first from both sides. Right, so that will be, sorry, a 1200. My mind was working. 800 minus 1200 is 400. So I'll have a negative 400 when we subtract 1200 from both sides. Now notice there's a couple ways to go here. I think the easiest way to go, I might just try some cross multiplication here just to keep it easy. So let's come on up over here, and we have negative 400 e to the 0.8t equals negative 1140. Let's divide both sides by a negative 400. Let's go ahead and get that. So gosh, I wish I could get you. Ava, can you get your calculator going and get that to me? That would be great. I really miss you guys. How about you, Anna? Matthew, Joe, can you pop this in for me? I'm always saying, hit your buttons on the calculator. Let's take a look. This is a 2.85. We know that we need to take the natural log of both sides. And we get 0.8t equals the natural log of 2.85. I might just write that. You can see we're going to divide both sides by 0.8. We'll just do all that math at one time. There we go. Let's pop that in. Let's see, the natural log, 2.85 divided by 0.8. And so that would be at 1.309 years. is when K is 0.8, that is when the calf would weigh, what were we start, 800 pounds. Okay, let's do our C here. Let's see, what is the maximum weight of the animal for each of the models? We're just doing it for 0.8. So again, let's just take a look here. Here's the weight formula. So what does it mean when they ask, what is the maximum weight? To me, that would be at some time, the animal's weight is going to be at a maximum. So I'm actually looking for, what would this be, Maddie? Hi, Maddie. This would be the limit as t approaches infinity, right, of this expression here. This is the weight expression, and we want to know as time approaches infinity, what would be the maximum weight of the animal. So let's go through this logically here. So notice, maybe Angela, you can do this with me, right? When we put infinity in for time here, e to the 0.8 times infinity, that's going to make this denominator very large, pushing this fraction to 0. So we would have 1200 minus 0. So the answer is actually that easy if you're able, to see it the way we're looking at it, and that would be 1200 pounds would be the maximum that this the calf would end up weighing. And that is the end of our problem. If I didn't get to include anyone's name in the video, I'm sorry, but I am thinking of you.